Swayam Prabha. Digital India. Educated India.
Okay, so good morning, everyone. My name is Piyush Rai. I'm from IIT Kanpur. Theme of today's lectures is going to be probabilistic modeling. So there are 3 lectures that I'm going to deliver today. In the first lecture, we'll look at the basics of probabilistic modeling. So that is why this lecture is titled Introduction to Probabilistic Modeling. So as I said, there are going to be 3 lectures. In this lecture, in the first lecture, we'll talk about some of the basic concepts in probabilistic modeling. In lecture 2, we will look at probabilistic models for doing regression. So you might already have seen regression or linear regression in one of the previous lectures. In second lecture today, we will look at how we can solve regression problem taking a probabilistic approach. Okay? And in the third lecture, we will look at how to do classification using probabilistic models. We will also look at other type of probabilistic models, namely the latent variable models. And I will also talk about very briefly about some of the other topics in probabilistic modeling that we will not have time to go over. Okay? So without further ado, let's start with the basics of probabilistic modeling. Okay? So by the way, so we can keep it interactive. If you have questions at any point, feel free to interrupt and ask. Okay? So let's get started. So I'll start off with a very simple toy problem for parameter estimation, where we are trying to estimate the mean of a Gaussian distribution. Okay? So how many of you have not heard what a Gaussian distribution is? I guess you all have seen Gaussian distribution in some form, right? So the problem setting is as follows. So let's assume that we have some data consisting of n scalar valued observations that I'm denoting by x1, x2 up to xn. So these are n observations that we have observed, okay? And then we will assume that each of these observations is drawn independently and identically distributed from a one-dimensional Gaussian distribution defined by a mean mu and variance sigma squared, right? So we are assuming that all these observations, x1 through xn, are coming from this normal distribution whose mean is mu and whose variance is sigma squared. Okay? And a Gaussian distribution looks like this bell-shaped curve, as you can see in the slide. And we are assuming that we are given a finite number of observations, and we are assuming that these observations are coming from this Gaussian distribution normal mu comma sigma squared. Okay, so this problem is clear, this problem setting. Okay. Now, the task that we have here is that we don't know what the mean of this Gaussian distribution is. Suppose, and that is what we would like to estimate. Okay, so our problem will be very simple. We are going to estimate the mean of this Gaussian distribution. For simplicity, we will assume that the variance of this Gaussian is known. Okay, so we will just simplify although there could be 2 unknowns, both the mean and variance both could be unknown. However, we will simplify things and we'll assume that the variance is known, only the mean is unknown, mu is unknown, and that is what we are trying to estimate using these observations x1 through xn. All right? So how do we solve this problem? Okay. Now, if you have seen other basically models for analyzing data or learning from data, we sometimes define a loss function that measures how well our data fits the model, and then we minimize or optimize that loss function. Okay. So we can follow the same approach, and we can define some sort of a loss function for this problem, and try to minimize that loss function with respect to the parameter that we are learning. So the parameter that we are learning is mu. So let's define a loss function and try to minimize or optimize basically that function with respect to mu. Okay? Now for this problem, what would be an appropriate loss function? Well, one choice for this loss function could be to define it in terms of the sum of squared deviation. So we can say that let's measure how far each data point xn is from the mean of this Gaussian. Okay, and let's take the squared basically quantity and then sum it over all the data points. So I'm defining this loss function L of mu equal to sum over all observations xn minus mu whole squared. Okay, so this is a reasonable loss function. It is measuring the deviation of every data point from the mean that we are trying to estimate. Okay, so this can be a plausible loss function. Of course, there can be different other type of loss function that you can define, but this is sort of a reasonable loss function like that you can think of for this problem. Okay, all right. So we have defined a loss function. It's clearly a function of mu. Now, what we can do to estimate this parameter mu? Any suggestions? What will be the optimal mu? How would we solve for mu? We optimize, we take derivative with respect to mu, set it to 0, and then the optimal mu we can find, right? So if we do that, we'll get an estimate of mu. So if you can do this exercise, it's a couple of lines of simple calculus. And if you take derivative with respect to mu, set it to 0, you will get the estimate of the optimal mu, which I'm denoting by mu hat as the sum of all the data points, sum of all the xn's divided by n. Okay? So this is what you will get as an estimate of the mean. And this is nothing but the empirical mean of the data. You're just taking all these n observations that you have, and then you're taking the empirical mean. Okay? So if you try to estimate the mean using this simple approach of defining a loss function and then optimizing it with respect to mu, then this is the solution that you will get. Okay? Simple enough? Right. Now, can we also pose this problem as a probabilistic modeling problem? Okay, so can we pose and solve this problem taking a probabilistic approach? Okay, so that is what we are going to see. So we have not done anything, in terms of a probabilistic model. So we have just defined a loss function. There is nothing probabilistic as such about the loss function. The loss function is just like this sum of squared deviations. Okay, but how do we pose this problem as a probabilistic model and then solve it to estimate mu? So that is what we are going to look at next. Okay. So before I do that, just so we all are on the same page, let's look at what a Gaussian distribution looks like. So for simplicity, I have given you an example of a univariate Gaussian distribution, which is basically a Gaussian in one dimension. So a Gaussian distribution is defined over real-valued scalar variables, random variables x. It is defined using a mean, mu, and a scalar-valued variance sigma squared, which is positive. And the form of the Gaussian distribution is basically n of, so normal distribution x with mean mu and variance sigma squared is 1 by square root 2 pi sigma squared, exp of minus xn minus mu squared by 2 sigma squared. So this is the expression of the probability density function of a Gaussian distribution. And the Gaussian has this shape, so depending on the values of mu and sigma, you can have different looking, Gaussian distributions. Okay, so typically, so the mu is where the mean of the Gaussian is, right? And that is where the Gaussian has the largest, probability density. So you can see that the peak of the Gaussian happens at the mean, mu. Okay, so this is the expression of a Gaussian distribution. So this will be used again and again in the coming slide. So it's important that you understand what the expression looks like. So again, the expression is, it has exp of minus a quadratic term. So quadratic term is like xn minus mu squared divided by 2 sigma squared. Okay, so this is what a Gaussian distribution looks like in one dimension. All right. Now let's go back to the original problem where we were trying to estimate the mean of this Gaussian distribution. So in the probabilistic approach, what we can do is we can start by writing down the probability. So we have observed these n data points, x1 through xn, right? So if we ask what is the probability of all these n observations, so we can compute that. And so we can define this probability as P of capital X given mu. So capital X denotes all the n observations. x1 through xn collectively I'm calling capital X. Okay, so P of X given mu. Since we are assuming that the observations are all independent, we can just write down this probability as a product of the individual probability. So let me just use the stylus to me. So this thing, as you can see, there is a product over all the n observations. So P of xn given mu. So each of these terms is the probability of one data point xn given the parameter mu. Okay, and we have a product because these are independent observations, so we can just multiply the probabilities. Okay, and we already have seen what the Gaussian distribution looks like. It's this for each observation. I have this as the expression. Okay, and we have a product. So note, so this is P of x given mu is basically the probability of observed data as a function of the parameter mu. Okay, this quantity is also known as the likelihood. Okay, so what is the likelihood of the parameter? So given the observed data, so this is also known as the likelihood. Now, again, what was our original task? Our original task was to estimate mu. Okay, so given this probability of data as a function of parameter mu, what would be an optimal value of this parameter mu? Okay, so again, what we can do, we can try to, so what is the optimal mu here? Okay, so we have the probability of data as a function of mu. See, the optimal mu intuitively would be one that maximizes this probability, right? So optimal mu will be one that maximizes the probability of observed data. So what we can do here, we can try to find the optimal mu as and set it to the mu that maximizes P of x given mu. Okay, so we can solve this problem as mu hat as argmax, which is basically maximizing the probability of x given mu. And so this argmax, so I am maximizing P of x given mu as a function, with respect to mu. And instead of maximizing P of x given mu, I can also maximize log of p of x given mu, because log is a monotonic function. So, and log simplifies this calculation because I have an exp function here. So if I take a log of that, the exp will go away and I'll just have a simple quadratic form. Okay. So both these problems are equivalent. Either I maximize log of p of x given mu or maximize log of p of x given mu. Okay. So if I look at log of p of x given mu, I have already defined p of x given mu. So if you take log of this log of product turns that into a summation over many of the squared quadratic terms. So this is what you will get when you take the log of this quantity at the top. Okay. So this quantity that we have here, if you take log of this, this product will turn into a summation. Okay. And since we are doing this maximization with respect to mu, any term that only contains sigma can be ignored. Okay. Because sigma is treated as a constant. Okay. So the relevant terms that we will be left here will be only terms that have xn minus mu squared. Okay. And note that we have a negative xn minus mu here in the exponent, right? So if we take so argmax becomes argmin here, okay? So mu hat will be again argmin of this squared sum, the sum of these squared deviations, okay? Note that this is the same problem that we had in the beginning, right? So where we defined an ad hoc loss function as a sum of squared deviations. Okay, and here also we are starting with a Gaussian distribution, the expression, and then we are doing we are maximizing the probability of data, and we are getting the same expression here as well, right? Now this procedure that we have followed, that we have written down the probability of data, which is also known as likelihood, and we have tried to maximize the likelihood with respect to the parameter we are learning. This procedure is known as the maximum likelihood estimation, or MLE in short. Okay, and it's called MLE because you're trying to find the parameter that maximizes the likelihood. Okay, which is why the name is maximum likelihood estimation. Okay, so as I said, because the final objective is the same as what we defined earlier in the loss function minimization approach, it's not surprising that we'll get the same solution. If we minimize this with respect to mu, we'll get again mu hat as the empirical mean of the data. Okay, because we essentially have the same objective here. Right? So we saw that we arrived at the same objective taking a probabilistic approach. In the previous case, we did not have a probabilistic model. We just defined a loss function, optimized it, and we obtained this solution. In this case, we defined a proper probabilistic model for the data, and then we maximized the probability of data given parameters, and we found this solution. Okay. So what is the point of this whole exercise? If all we are doing is that we are doing maximum likelihood estimation, which is giving us the same solution as the loss function based approach, why bother about doing all this basically? Okay. So what did we gain here by taking a probabilistic approach? Well, we'll get the answer shortly. Okay? But at least we have seen that we can pose this problem in a probabilistic way. We can formulate a maximum likelihood estimation problem, and we will have a solution for the original problem. Okay? So what other benefits this approach gives us, that is what we are going to look at shortly. Okay? Any questions at this point? Okay, hopefully it's all basics, so there are no questions at this point. Okay, so let's make the problem slightly more interesting. Okay. Now, suppose we have some sort of prior knowledge about the parameter that we are learning. So what is the parameter that we are trying to learn? The mean of the Gaussian distribution, mu, right? So suppose someone came and told us that this parameter mu that we are trying to learn is close to this value mu0. Okay, mu0 is some number that your friend came to you and then told you that, okay, I believe that mu is close to mu0. Okay. How can you use that information in your parameter estimation problem? Okay. So how would we do that? Well, you all have heard about regularization, right, in machine learning models. So what we can do, we can now add a regularizer of the form mu minus mu0 squared, okay, in the original objective function. So what was our original objective function? Well, it was this squared, sum of squared errors, right? So what if we just add another term, mu minus mu0 squared, and minimize that, the whole objective instead, okay? Okay. So now what we are doing is that we have this loss function, and we have a regularizer which kind of promotes mu0 to be close to mu0 because we are minimizing this objective, right? So you must have seen function optimization problems where you have a loss function and a regularizer. So this is a very similar kind of an approach here. Okay. Now, if you solve this optimization problem, again, it's just a couple of lines of calculus, you will get the solution, the optimal mu hat as sum of all the xn's plus mu0 divided by n plus 1. Okay, so it's very similar to the previous solution where we had sum of xn's divided by n, but you have a mu0 in the numerator and you have a plus 1 in the denominator. Okay, so if we incorporate this prior knowledge that mu is close to mu 0, then our solution becomes this. Okay. So as you can see, our estimate of mu, the mean, has kind of shifted towards mu 0 because we are adding a contribution mu 0 and then dividing it by n plus 1 rather than n, right? So our estimate is kind of shifting towards the prior knowledge we had. Now, if we ask this question that what happens when the number, so what is capital N? The number of total number of observations. If you look at the solution that we have, for mu hat now with the prior knowledge, what do you think will happen when N becomes very, very large? What will be mu hat approximately? It will be sum of xn divided by n, because if n is very large, then n plus 1 will n will just like be roughly equal to n plus 1, right? So, and this summation would also be kind of dominated by some of the observations. The mu will be kind of washed away, right? So if n is very large, then the effect of this prior information is kind of diminishing it. So it's not really contributing, right? So when does this matter more? So when does the information matter? When does the prior matter more? The prior knowledge. Well, when you don't have enough data, if you have very small number of observations, then this extra information that you have, makes more sense. Okay, but as n becomes very, very large, then this information is kind of irrelevant. Okay, but especially if you don't have much data, then this does become somewhat important. As I said here, we wanted to incorporate some prior knowledge about the parameter that we are estimating, right? And we again kind of took an ad hoc approach. We just took the objective function, the squared, sum of squared errors, and we added this regularizer in this ad hoc way. We said that, rather than minimizing this sum of the squared deviation, we'll just add the regularizer, and that will give us the solution, this solution, right? Now, can we do this thing again in a more principled or probabilistic way? Okay, so can we add this regularizer in a more proper sense, rather than just saying that, well, let's use this as let's use mu minus mu 0 as our regularizer. Okay, so can we do this in a more formal way? It turns out that yes, there is a way we can impose or incorporate this regularizer in a more formal way, and that is using something called a prior distribution on the parameter that we are learning. Okay, so I'll talk about what a prior distribution is. So it turns out that you can add a regularizer like this by taking a proper probabilistic approach, and that is when the prior distribution comes into picture. Yes. Yeah, so when n is large, if you look at the solution, right? So if you have too many observations, like if you have lots of observations, then roughly the contribution of mu 0 will not be that much. So your solution will be roughly the same as the solution that you had without the prior knowledge. Okay. However, if n is not very large, then of course the role of mu will be more important. Okay. Okay. So what is a prior distribution? So suppose we have some sort of a probabilistic belief about what our parameter mu looks like, okay? And that belief is basically before seeing any data, right? So suppose we have not yet observed the data x1 through xn, right? So and we have some sort of a belief about what the parameter looks like, what kind of values it takes, or what kind of range the values lie for the parameter that we are trying to estimate. Okay? And I'm explicitly mentioning that this belief is in a probabilistic sense, okay? So we will not say that mu is close to mu 0, right? So, but rather, we would say that our belief is modeled by a Gaussian distribution on the parameter mu, okay? So we will say that a priori, we believe that the prior distribution, the mu has a prior distribution given by another Gaussian with mean mu 0 and variance sigma 0 squared. And Gaussian distribution, we have already seen what it looks like. So we will say that our parameter mu has a prior distribution which is given by a Gaussian with mean mu 0 and variance sigma 0 squared. So that is our prior belief about mu. And what this prior is telling us is that it's saying that we kind of believe that mu is close to mu 0, the mean of this Gaussian distribution, and it has some spread or uncertainty around that mean. So, and the spread is kind of captured by this quantity sigma 0 squared. Okay, so this is kind of a probabilistic way of specifying what the parameter looks like. Okay, in the previous case, we simply said that mu is close to a mu 0, but now we are saying that no, we have some sort of a distribution over mu, and it's a prior distribution. We have not yet seen the data. We are just saying that it's a mu kind of lies, lies under this Gaussian distribution that has a mean mu0 and it has a variance sigma 0 squared. Now, you might ask, why did we choose the Gaussian distribution as a prior? Why not any other distribution? Okay. Sure, you can use other type of distribution as priors, but the Gaussian distribution has some interesting properties that we'll look at shortly. One of the properties is that it is easy to manipulate, computationally, and it also makes sense in most cases. For instance, so if you think of a Gaussian distribution, it is a distribution over real numbers, okay? And the mean that we are trying to estimate is also a real number, okay? So it's not totally unreasonable to assume that it's basically a reasonable distribution. Okay, so we have a prior distribution, which is basically our a priori belief about the parameter that we are estimating. So how do we now update our belief about the parameter once we see some data? Okay, so we start with no observations, right? We only have this belief that mu looks like a Gaussian distribution. Mu looks like coming from a Gaussian distribution. But once we have seen these n observations, x1 through xn, how do we update our prior belief? Okay. Essentially, like we are trying to learn now mu. Once we have seen some data, we would like to learn mu. Now, in order to do that, we have to combine this prior distribution over mu with the likelihood model we had for the data. We had P of x given mu as the likelihood, and then we have the prior distribution P of mu. So in order to update our belief about the parameter, we have to somehow combine the prior distribution with the likelihood model. Okay? How do we do that? Well, that brings us to the well-known Bayes rule. Okay, so the Bayes rule is a fairly simple rule. All it says is that if you have something like the probability of A given B, you can get the probability of B given A using that. Okay, so we are trying to do something like that in this problem. We are trying to estimate the probability. So using the Bayes rule, we can define a posterior distribution of mu, and the posterior distribution is defined by P of mu given x. What is the distribution of mu having seen data or conditioned on the data? Okay, and the Bayes rule simply says that P of mu given x is P of x given mu times P of mu divided by P of x. So this is just the simple application of Bayes rule. In the numerator, we have the likelihood and the prior, and in the denominator, we have just P of x, which is also known as the marginal probability or marginal likelihood of data. Okay. So the Bayes rule allows us to combine the likelihood and the prior to get the posterior distribution of mu, which is nothing but our updated belief about mu once we have observed the data. Because now we are saying that it's no longer just P of mu, but P of mu conditioned on the observed data. And this is what we are trying to estimate, right? So we want to update our belief about mu having seen the data. Any questions on this before we move on? Okay. Okay, so we have observed n values, right? So we have x1 through xn. So this capital X is all the observation that we have, in our data. So in the beginning, I talked about we have n observations that we are assuming that they are coming from the Gaussian distribution. Okay, so this capital X is all those n observations. The set of. So I defined that. So P of xn given mu is a Gaussian distribution, right? So the PDF, if we go back to the previous, slide. So. Right. So each observation, P of xn given mu, is a Gaussian distribution, right? So we have n observations. Each observation is coming from the same Gaussian distribution, right? So which is why we have a product over these n quantities. Okay. So the overall probability of capital X given mu is just a product of the individual probabilities. So it's actually not just probability density, because we are dealing with continuous distributions. Okay. So. Right. So we have now defined a posterior distribution of mu, okay, given x, and that's given by the likelihood times prior divided by the marginal probability of data. Okay. So if we have the posterior distribution of mu, what would be the most likely value of mu? So now we have a distribution over mu, right? So if I ask what is the most likely value of mu? Well, one option would be to look at the maxima of this distribution, where this P of mu given x attains its maximum value, because P of mu given x is a function of mu, right? So you can just try to maximize this function P of x given mu with respect to, so if you maximize this posterior probability with respect to mu, then it will give you an optimal value of mu, right? So what we can do here, Right. So what one option to find the optimal mu now would be to set mu hat as the point mu that maximizes this posterior distribution. So argmax of P of mu given x. Right. So so if we do this, so note that the point mu that maximizes P of mu given x is the same as maximizing P of x given mu times P of mu. Right? Because the denominator, so we are maximizing this posterior distribution, and the denominator does not depend on mu. P of x does not depend on mu, right? So maximizing P of mu given x is equivalent to maximizing the product of the likelihood and the prior. Clear? Again, we can play use the log trick. We can say that rather than maximizing this product, we can maximize the log of this product. Again, because log is monotonic. And when we maximize the log of this product, so log of this product turns into a summation, right? So if I maximize log of P of x given mu times P of mu, then it becomes log of P of x given mu plus log of P of mu. Okay? So mu hat is argmax of the sum of log likelihood plus log of the prior distribution. Okay? Now if you compare this with the previous formulation of maximum likelihood, it's very similar to the previous formulation, except that we now have this log of prior. In the previous case, we just had argmax log of P of x given mu. That was maximum likelihood estimation. But now we have log of P of x given mu plus log of P of mu. So in this problem, all we have is that we have this additional factor log of P of mu. So we have an optimization problem where we have this additional factor of log of the prior distribution. Right? This approach of finding the optimal mu by maximizing the posterior distribution of mu, okay, which is what we are doing here, is also known as maximum a posteriori estimation, because you are you're finding the mu that has the maximum posterior probability. Okay, so this argmax of P of mu given x is also known as maximum a posteriori estimation. Okay. The previous approach that we talked about was called maximum likelihood estimation, because we only maximize the likelihood, but now we are maximizing the posterior distribution of parameter. Okay? And the basic difference between maximum likelihood estimation and maximum a posteriori or a map estimation is that in the map estimation we have this additional term log of P of mu. Okay? Other than that, it's pretty much the same as log of P of mu. Okay, so P of mu we already defined, right? So we defined a prior distribution in the previous slide. So we said that P of mu, the prior distribution over mu, is a Gaussian distribution. Okay, so when you take the log of this, it will be log of this quantity that we have, log of this Gaussian distribution. Okay, so all you have to do is write down the log of this, simplify the term. So log will eat the exp term, right? So you'll just have this mu minus mu 0 squared divided by 2 sigma 0 squared. Okay, so all you have to do, I'll show you the final expression shortly. Okay, so what you have to do in order to get mu hat, you have to solve this argmax problem where the objective function is log of this likelihood plus log of the prior distribution. We already have defined log of the likelihood and the log of, we have already defined the likelihood and the prior distribution. Both were Gaussian. So this likelihood was product of Gaussians, product of n many Gaussians, and the log of prior is also Gaussian. So the moment you plug in these two expressions, I have not shown the derivation, but it should be apparent, because when you look at the log of the likelihood, we will get a term that looks like sum of xn minus mu squared by 2 sigma squared. And the log of prior distribution will look something like mu minus mu 0 squared divided by 2 sigma squared. And note that I have an argmin here instead of an argmax, because these terms are originally negative. So I have just subsumed the negative. So the negative makes it argmin from argmax. Okay. Note that, when I have simplified it, I have ignored any terms that do not depend on mu, right? So, so I have only so any term that does not contain mu, I have removed, because it does not matter in this maximization problem. Yeah.
But if we don't even know mu, how do we expect to know sigma?
Okay, so we made an assumption in the beginning. Right? In the very first slide, I said that we are simplifying our task. We are saying that let's assume that sigma is known to us. Okay. So suppose someone told you what sigma is, right? Okay. Now the thing, you can estimate sigma, but just for simplicity, I'm assuming that sigma is known. Okay. If sigma is not known, then the problem has to be solved iteratively, where you estimate one, assuming that the other is known, and then go back and forth. Okay. So anyway, so the problem of estimating mu reduces to argmin of the sum of squared deviations. So note that here we all have explicitly kept sigma squared, right? Because now So you can't just ignore sigma squared because it does appear in the final solution. In the previous case, when we were just doing maximum likelihood, the sigma squared used to get cancelled, so you could just ignore the sigma squared. Okay? Because if I don't have the second term, then maximizing only the sum of the squared divided by 2 sigma squared is equivalent to minimizing the numerator itself. You can ignore the sigma squared. But in this overall formulation, sigma squared needs to be there in the final solution. So anyway, so we have mu hat as the argument of the sum of these two basically terms. And again, all you have to do is take derivative with respect to mu, set it to 0. It's not at all complicated. The final solution that you will get will look something like this. So pay attention to the form of the solution. Again, it's very easy to derive. You just have to take it's simple quadratic function of mu. Mu is assumed to be scalar, so you don't have to do any matrix or vector algebra. You just calculus. You just have to do simple scalar valued scalar calculus. So the final solution of mu hat, which I'm denoting by mu hat map, just to distinguish it from the MLE solution that we had. It will have this form. So it will look like sum of the all observations, xn divided by sigma squared plus mu 0 divided by sigma 0 squared divided by n by sigma squared plus 1 by sigma 0 squared. Yeah.
We already know variance, right?
Yes.
Then why is there a sigma square and sigma not square?
Okay. So sigma square is the variance in the distribution of the data. Right? Sigma 0 squared is the variance in the prior distribution of mu. Okay? So both.
Sigma square we calculated, sigma not is 3.
Okay, so both are known actually. So in fact, in this problem, even mu 0 and sigma 0 are known. So again, I'm keeping it keeping the setting very, very simple. So I'm assuming that everything else is known. Mu 0, so we said that we have a prior distribution over mu, right? So P of mu was normal with mu 0 mean and sigma 0 squared variance. We are assuming that both mu 0 and sigma 0 are known. Likewise, sigma square in the likelihood term was known. Okay, so the only unknown in this problem is mu. Okay, so everything else is a constant. Okay, it's known. You can estimate. So in fact, you can pose it in a more sophisticated way. You can learn all these things, but it will just complicate things, which is why I'm just keeping it simple. Okay. Okay, so just to summarize, so the map estimation problem for mu will have this argument will have an argument of this objective, and the solution looks like this. Now pay attention to this form. So we have a term in the numerator that looks like a sum of all the observations divided by sigma squared plus mu 0 divided by sigma 0 squared divided by this term n by sigma squared plus 1 by sigma 0 squared. Okay? So that's our map estimate of the parameter that we are trying to learn. Again, as you can see, if we have lots of observations, then the second terms in the terms can be ignored, and you can actually just have the maximum likelihood-like solution. But if you don't have enough observations, then it's important to have these terms here. Any other questions on this part? Okay, so we have seen that we can actually incorporate some prior knowledge about the parameters that we are estimating in a proper probabilistic way by assuming that the parameters that we are trying to learn have a prior distribution. Okay? And then we can use the Bayes rule to combine the likelihood distribution and the prior distribution, and we can find a map estimate of the parameters. All right?